Okay, so now what I'm going to do is that I will walk you through the exploitme001 C program lab exercise for this week. All right, so the first thing we need to do is that we need to compile our exploitme001.c program. Right, so once compiled, we will want to put this compiled program into GDB for analysis. All right, so a quick recap of what we are trying to achieve here. All right, so if you look at right, so this is the memory stack that I've hand-drawn for exploitme001C program. All right, so if you recall, this exploitme001C program only has one function, the main function. All right, so when main function runs, a memory stack will be created. Right, so a quick recap, when the main memory stack is created, the first thing that goes into the stack would be arguments. All right, arguments followed by return address. Return address is at the location of EBP plus 4. The next thing that goes onto the memory stack is actually save frame pointer. All right, so save frame pointer is at the EBP location. Save frame pointer is always 4 bytes. Return address is always 4 bytes. And what comes next, the remaining part of the stack, is what we call the stack content. All right, so stack content will actually stores your information like variables, buffers, and paddings. All right, so if you look at this diagram, all right, higher memory is always at the top. Lower memory is at the bottom. All right, so stack grows downwards. I mentioned earlier that the first thing that goes onto the memory stack would be function arguments. Function arguments goes up right at the top of the stack. Next thing is return address, followed by save frame pointer. All right, so it's stacked from the top to the bottom. All right, so that's why we call it stack grows downwards. And this is the reason why we call it stack grows downwards. All right, so the challenge here, all right, so the challenge for this exploitme001C program is that we have, if you look at the code again, all right, so just let me bring this up. Cat exploitme001.c. If you look at this C program, it's pretty straightforward. There's actually a buffer above variable that is defined. All right, so the buff variable would always get started somewhere in the middle of the stack content zone. All right, stack content zone will actually be between your EBP to your ESP. All right, so this is your entire stack content zone. And your buffer location would always start somewhere in the middle. All right, so the challenge in buffer overflow attacks is that you will need to be able to override return address. You will need to override return address. All right, and the key trick is that you will need to identify the start location of your variable buff. Because if you're able to discover the start location of your buff variable, you would be able to calculate how many bytes are needed to override the return address. All right, because right now we don't really have a full grasp. We know that our buff might start somewhere along here. All right, so we are not really certain how many bytes is needed before we can actually overwrite the return address. So this is the first challenge that we need to resolve. So how are we going to discover or calculate the number of bytes needed to overwrite return address for this specific piece of exploitme001C program? All right, so it's pretty straightforward. There are multiple ways to do things, all right, to do this. So I'll show you one of my favorite ways. Okay, so we have put exploitme001 into the GDB. All right. So right now we are going to look at the main function assembly code. Right. So I mentioned in class earlier, when you compile a C program, it converts your C codes into assembly instructions. All right. So this chunk of C codes is essentially converted into this chunk of instructions, assembly instructions. All right, so usually we will want to put in breakpoints right after the vulnerable function, right? So the vulnerable the buffer overflow vulnerable function is actually string copy. All right. So if we look at the assembly code, all right. So this is the line, right? This is the line where the string copy function is being called. We can actually see call string copy. All right. So a good place to put in breakpoints would be right after string copy. Okay, so we can actually put in breakpoint. Oops, not this. Right, so we will want to put in the address for the instruction right after string copy. All right, so we have set a breakpoint right over here. All right, so right now I'm going to run the program. Right, so I would first start off with running the program by giving a user input, by feeding the program with a user input of maybe 4 A's. All right, so if I run with 4 A's, it stops at my breakpoint. All right, the breakpoint right after string copy. Because what string copy does is that it takes my user input AA, and it tries to copy to buff. All right, it tries to copy to the buff variable. All right, so if we set a breakpoint here, when we look at the memory stack, we should be able to see where our AAA, where our user input is actually located in. All right, so if you look here, we are at our first breakpoint. All right, so we need to be able to find a way to print out the memory stack. All right, so we want to print out the memory stack all the way from the location ESP till the return address so that we can have a good full view of this region. All right, this region all the way from return address to ESP. We want to be able to print out the memory stack content for this area. All right, so how do we do so? Right, how do we know how many bytes to print? How do we know how many bytes to print? All right, so it's pretty straightforward. We can see that at the bottom of the stack is always the ESP register. All right, so ESP is always pointing to the bottom of the stack. And right at the top of the stack is always EBP plus 4. All right, so if we are able to discover, the memory address for ESP and the memory address for EBP plus 4, we would be able to calculate the difference and derive how many bytes exactly is there between ESP and EBP plus 4. All right, so I'll quickly show you how to do it. All right, so to print out the memory address for ESP, you can actually simply do x/xw $exp. All right, so essentially this is the memory address of ESP, and this is the value that is being stored within ESP register. All right, and we will print out EBP plus 4. Right, so this is the memory address for EBP plus 4, and this is the value that is being stored within the EBP plus 4 location. All right, so this memory addresses I've mentioned in class earlier that these are hexadecimal. All right, so it's pretty straightforward to calculate the differences between both the addresses. All right, so all you need is a calculator. All right, so open up your calculator, set it to programmer mode. All right, so all you need to do is to take the last 4 characters. Right, so maybe if you look here, so I can actually take F13C. You can actually take F31C minus F1 F0. All right, so we get 12C. And if you look at decimal, right, essentially 12C converts to 300 bytes in decimal. All right, 300 bytes. So basically, look here. All right, so we take F3 because we managed to discover the memory address location for EBP plus 4. Right, so the memory address location for EBP plus 4 is BF FF F3 0C. The memory address location for ESP is BF FF F1E0, right? So all we need to do is to take F30C minus by F1E0, and we get a difference of 300 bytes. So essentially the region from EBP plus 4 to ESP is 300 bytes. All right. So we know that if we print out, we can actually print out this region by printing 300 bytes from ESP. All right. But this 300 bytes does not include the return address values. All right. So if we want to print out the return address values as well, we need to take 300 bytes. We need to take 300 bytes plus 4. All right. So that would mean that to print out the entire memory stack, starting from the ESP, we need to print 304 bytes upwards to be able to print out everything all the way from ESP to the return address. All right, so how are we going to print out 304 bytes from ESP? Right, so pretty straightforward. I mentioned in class that this is a 32-bit operating system. All right, so one hex words, right? So one hex words is essentially 4 bytes. All right, so how many words do we need to print to be able to print out the entire memory stack? So all you need to do is to take 304 bytes, divide by 4 is 76. All right, so to print out 304 bytes, we just need to do x/76xw ESP. All right, so what this does is basically it prints out 76 words. All right, so one word is 4 bytes. It prints out 76 words, which is 304 bytes, starting from ESP. All right, so this is your ESP. All right, so this is your ESP. This is your return address, which is EBP plus 4. And this is the 4 A's that we have entered earlier. So if you recall, when I run the program earlier, I actually run it with run space AA. I run it with 4 A's. So A is never stored on the memory stack as A. All right, it will be stored as hexadecimal on the stack. So an uppercase A will be converted into 41 in hex. You can refer to the hex table conversion or ASCII table to get a better understanding of how to convert an uppercase A into hex. All right, so essentially 41 is 1A. So I put in 4 A's. So A. All right, so my 4 A's are all here. Right, so I have actually put up a image, right, which might help you to understand better. Okay, so basically I printed out 304 bytes and I've showed you how to calculate 304 bytes. All right, so 304 bytes essentially is the entire stack, right? So I have printed out the entire stack all the way from return address to ESP, this region, all right? I've printed it out using x/76xw $ESP. All right, so the first value here is your ESP. ESP is always right at the bottom. It's always pointing at the bottom of the stack, which is the lowest memory address space. So that will be F1E0. All right, your EBP plus 4, which is your return address, is located here. All right, return address. So right now, we can see that our A is located over here. All right, F200. F200 is over here. So this is the start location of our buff variable. Right, so if you recall, buff variable, right? So buff variable, when you declare a variable, it will actually get allocated. It will get allocated somewhere between the region of EBP and ESP. You have no control of it. This is actually decided by compilers, right? Compilers, they have different ways of optimization, and the start location of buff variable varies. Right, so if you look here, we have actually determined that the start location for our buff variable is actually at BF F200, which is here. All right, so how are we going to calculate how many bytes do we need to overwrite the return address fully? right? So we need to overwrite all of this, right? We need to overwrite starting from here to here to here to here to here, all right, all the way to the return address. All right, so how are we going to do it? So if you look at what I've drawn, all right, so I've actually put in, okay, so our start of buffer variable is at location BF FF F200. This is the start of our buffer variable, right? So we need to overwrite all the regions that is highlighted in blue, right? So we need to overwrite this entire region. All right, so we need to be able to calculate how many bytes does it take from the start location address for buff variable to the end of the return address. All right, so how are we going to calculate that? It's pretty straightforward. All right, we use the same technique. We can actually take EBP plus 4 memory address minus the buff variable start address. All right, so if we do it that way, we will take F30C, right? So that is EBP plus 4, F30C minus F200, right? So that would be in decimal 268 bytes, right? So 268 bytes is the distance away from the start of my first A all the way until the end of the safe frame pointer. All right. So this 268 bytes does not include the 4 bytes return address. All right. So to fully overwrite the return address, we need 268 bytes here plus 4 bytes. So that would be 272 bytes. So we need 272 bytes to fully overwrite the return address. So how are we going to prove it? All right, pretty straightforward. So we are going to rerun our program. Right, so this time I'm going to run my program. Instead, so earlier I ran my program with 4 A's. So right now I might want to run it with 272 A's. All right. So I'm going to run my program using Python. All right, Python -c print maybe A. All right, so maybe I'll print 268 A's. So earlier, if you recall, I mentioned that 268 A's would actually overwrite the start of buffer variable all the way until the end of safe frame pointer. All right. So let's write 268 bytes of A so that we can actually overwrite A's all the way from here to EBP, end of EBP, right? End of EBP. All right. Then we will write another 4 bytes of B. All right. So now I will run the program with 268 A's and 4 B's. All right. Let's see what's going to happen. All right. I'm not going to stop at the, oh, actually I'm at the breakpoint. So right now let's reprint the stack, right? So we are going to print the stack out again. So we are going to print 304 bytes from the ESP location. 304 bytes essentially is 76 hex words. All right. So we can see that, yes, 268 bytes will allow us to fully overwrite EBP. And additional 4 bytes is needed to overwrite the return address location. All right. Got it? So right now we know that we have this area, right? So we have this entire area to put in things, right? So maybe what we can do is that we can actually try to add in, because this is such a large memory space, we can try to put in some weird shell codes, function codes into this different location. All right, so maybe I can actually plant my shell code here, right? I can plant my shell code at this location, maybe at this location. All right, and when okay, so actually I can actually try to plant my shellcode at this location, right? Starting from here, and I can actually overwrite my return address to point to BFFF F130. All right, so that when the program exits, it will go to my return address, which is over here, F130, and my shellcode is located somewhere over here. Right, so you actually cause the program to go to my shellcode location, execute my shellcode when it exits. Because we have managed to control the return address, so we might be able to do something like this. All right, so I'm going to demonstrate that in a bit. Okay, so if you look at your lab worksheet, all right, so there is this exploit code that is provided to you. All right, so I'll explain this in a bit. All right, so I will need, before I explain that, I was just set a breakpoint. All right, so maybe just ignore me. All right, I'll go back into GDB. I will set my breakpoint at right after string copy. Right, so I'll set a breakpoint and I will run this. I'll run the program with this string. All right, so basically it prints out string. Right, so what this is going to do is that it's going to print out 216 bytes of hex 90 followed by this string. All right, so just for information, this string is my shellcode. All right, so this string is my shellcode that I'm going to push it onto the memory stack. And this is, I'll print out additional 20 A's and I will actually overwrite the return address with this specific address. All right, so I will run this program and I will show you within the memory stack later on to really explain what exactly is going on. All right, so right now I'll run it and the program pauses at my breakpoint. So right now I'm going to print out the memory stack again. All right, I'm going to print out the memory stack because it's still 304 bytes. Okay, so if you recall, what have we done? All right, so we run the program with 216 bytes of hex 90. All right, so this hex 90 is here. All right, and then I actually input 32 bytes of shellcode. All right, 32 bytes of shellcode. This shellcode is provided to you in the worksheet. All right, 32 bytes of shellcode. And then I put in another 20 bytes of A's before I overwrite the return address with this address. All right, so what is this address? So this is BFFF170. Right, so this is essentially pointing to this location. All right, this specific byte, hex 90. All right, so where am I pointing it to? Hex 90. So what exactly is hex 90? Hex 90 is essentially what we call the no operation. All right, the NOP, N-O-P. Right, so when CPU sees a hex 90, a NOP, what the CPU does is that it ignores it. All right, it ignores it and it skips to the next byte, skips to the next byte, skip to the next byte, all the way until it sees a byte that is not hex 90. All right, so basically, right, we have overwritten the return address to have our program exit and land on our NOP. Right, so this entire NOP region is what we usually call as NOP SLED, SLED, NOP SLED. All right, so we have configured, we have actually we have actually overwritten our return address to have it land at this NOP SLED when the program exits. All right, so essentially when the program exits, it will go to this specific location and CPU will ignore all the hex 90 all the way until it sees our shellcode. And the program will then run our shellcode. It will run our shellcode, giving us shell access. All right, so I'll just prove it to you. Because I have breakpoint set, right? So just let me rerun GDB and I'll rerun this. All right, so it gives us shell access. All right, so if we run it, we can actually run it outside of GDB. It's pretty straightforward. The /exploitme001. And what we need to do right. So we run it, right? So right now, we have managed to get best shell, right? We've managed to give ourselves best shell. All right, so why is this a problem? All right, so say for example, okay, so in most scenario, right, an attacker might get into a system, might get access to a system as a non-privileged user. All right, so when they get in as non-privileged user, they will need to find a way to privilege escalate themselves. All right, so when they get in, if you recall in the last few lessons, I mentioned about set UID and set GID. All right, so set UID, set GID is basically to let the user who run the program to have the same privilege as the file owner. All right, so basically, let's try to imagine that we have a program, exploitme001. All right, so exploitme, right? So this exploitme001, it someone actually mismanages the permission and gives it a set UID bit. All right, set UID bit. All right, and an attacker managed to get into the system as a user called non-root user. All right, so it's non-super user. It's not a super user. Super user would have a UID of 0. So I'm in as a non-root user. So how am I going to leverage this buffer overflow attack? All right, so I'm a non-root user. So what I need to do, what I want to do, I want to privilege escalate myself, give myself super user privilege. So how am I going to do it? Pretty straightforward. I'll just exploit the buffer overflow attack. Right, I'll run it. Boom. Right, I get the shell. So who am I? I'm a root, right? So earlier I'm a non-root user, but leveraging buffer overflow vulnerability, I'm able to privilege escalate myself and give myself root access. All right. So I hope that this walkthrough of the exploitme001 C program will actually help you to reinforce your learning for today. All right. So do have a look, listen to this recording, and go back to the lessons recording, finish up the lab, and let me know if you have any questions. Thank you.